During the 20th century, man created countless new materials. In this program, we're going to introduce you to two of them, plastics and synthetic textiles. But before we do, let's take you a few hundred degrees below zero to the kingdom of superconductors. A few thousand years ago, man attached stone fragments to sticks and used them as spears, arrows, or some kind of implement. That was during the Stone Age. Later, around 4000 BC, he began to hammer different metals to make his tools more effective. He learned how to make alloys from copper and tin. The Bronze Age had come into being. The great periods of history bear the names of materials because the activities and progress of man were, to a large degree, determined by the material he used. The technological feats of the 21st century will depend as much on new materials as before. In the field of energy, for instance, great hope has been put in superconductors. For a material to become a superconductor, temperatures have to be lowered several hundred degrees. It then acquires some astounding properties. No, this magnet is not doing transcendental meditation, nor is there anything magical about this experiment. The magnet is levitating owing to the unique properties of the disc it is floating over. The disc could be metal, ceramic, or even plastic. What really counts is the fact that it's been made superconductive. And this is no small feat, because not one of these materials would exhibit superconductive properties under normal terrestrial conditions. For them to become superconductors, they must be kept at temperatures of about -200 degrees Celsius. That is, temperatures about 4 times colder than at the North Pole in January. Above such temperatures, superconductivity ceases, and the materials return to being simple conductors. But what exactly is superconductivity? Superconductivity is a phenomenon of physics whereby materials exhibiting superconductivity offer no resistance to electricity and total resistance to a magnetic field. In a simple conductor, the electric current is carried by electrons all following different paths. It's a real free-for-all. The result? The electrons keep bumping into each other and end up losing some of their energy. What then happens is that the metal heats up and some of the energy is lost. If you cut off the current, it takes only a few thousandths of a second for the electrons to lose all their energy and stop dead. Then the metal gradually cools down. However, in a superconductor, when an electrical current is induced, the electrons seem to line up 2 by 2. They form pairs, and their movement resembles a wave. Collisions between electrons are no longer possible, and the electricity flows without loss of energy. Superconducting materials do not heat up, and the electrons in them will circulate in the disk indefinitely. The physical changes materials undergo when they become superconducting make it impossible for a magnetic field to penetrate them. That's why this magnet is levitating. The magnet's field of force cannot penetrate the superconductor. A repulsive magnetic force is created that increases as the magnet gets closer to the disk. In fact, this magnet will continue to levitate for as long as the disk remains superconducting, that is, for as long as it is kept at a low enough temperature. While today we know materials that are capable of becoming superconducting at -150 degrees Celsius, that didn't used to be the case. When superconductivity was discovered in 1911, temperatures had to be lowered to -269 degrees Celsius before the phenomenon could be observed.
Scientists then set about looking for materials that could continue to be superconducting at higher temperatures. Later, in 1986, two Swiss scientists, Alex Mueller and Georg Bednorz, discovered a ceramic that could remain superconducting at minus 238 degrees Celsius. They were awarded a Nobel Prize for their discovery. A few months later, an American research team discovered a ceramic whose critical temperature was minus 150 degrees Celsius. This was a major step because this temperature can be reached with liquid nitrogen, a product that costs no more than milk. The fact that superconductors have nil electrical resistance provides many opportunities for a variety of applications. Owing to this property, superconducting materials can, for instance, create powerful magnetic fields. Superconductors are already being used in a number of medical imagery equipment where strong magnetic fields are required. Superconductors could also be used to store electricity, since the electricity induced in a superconducting disk never dissipates. A disk measuring 3 meters in diameter could store roughly 100 kilowatt hours, the amount of electricity required to satisfy the needs of an average family dwelling, heated by electricity for a 24-hour period on a cold winter's day. With regard to the second property of superconductors, namely their resistance to penetration by magnetic fields, this could eventually lead to the invention of protective screens for passengers traveling on trains, using superconductors as a source of power.
There exists another use for the strong magnetic fields generated by superconductors: magnetic power. Just imagine a train without wheels, without friction, ultra-fast, just sort of skimming over the tracks. Not only is it possible, the Japanese have already built a prototype. The Stone Age, the Bronze Age, the Iron Age. What age are we living in now? The plexiglass age? The nylon age? Or the plastic age? Nowadays, plastic is steel's greatest rival. Even if it is produced from crude oil, it costs less to make than steel. For some years now, we have been consuming almost as much plastic as steel. The first plastics made were semi-synthetic. They were manufactured in small quantities from remnants of cotton, camphor, and castor oil. But it wasn't until fully synthetic plastics were discovered, made from crude oil, that plastic gained the popularity it enjoys today.
In 1858, the first plastic object was invented. It was a pool ball. Since then, plastic objects have proliferated to such an extent that it would be impossible to draw up a comprehensive list of them all. In less than 120 years, plastic has conquered the planet and is more used than any other material. But what exactly is plastic? It all begins with petroleum, or crude oil. It is a complex mixture of different molecules, chiefly composed of atoms of carbon, hydrogen, oxygen, and nitrogen. To make plastics, certain oil molecules have to be selected. This is done through various chemical and physical processes. The molecules are then broken down into smaller ones called monomers. When similar types of monomers join together, they form a chain called a polymer. Polyethylene, for example, is a plastic commonly used in such things as shopping bags and containers. Polypropylene is a chain of propylene, a molecule containing 2 carbon atoms and 4 hydrogen atoms. There is an infinite variety of polymers. Depending on the nature of the monomer, how they are assembled, and how the long chains are arranged in relation to each other, the polymers will present very different properties. Polymers can even be designed specifically for a given application. Plastics can be made that are mechanically far more resistant than metals. To make them, a substance other than a polymer is added to the plastic to ensure strong adhesion among the molecules. The resulting composite is highly rigid and can have greater mechanical resistance than metal. The same process will yield plastics that will resist high temperatures. Some are even resistant to temperatures as high as 350 degrees Celsius. Plastic is a manifold material, capable of adapting, like a mutant, to all the demands of the modern age. That's why it's so successful. With plastics, everything seems possible. So even though they have always been considered electrical insulators, plastics can now be turned into conductors just by adding mercury to them, or into semiconductors by adding carbon black. Plastics have even been made into better conductors than copper, which is one of the best conductors of electricity. The advantage these polymers have in common is the fact that they have both the conductive properties of metals and those inherent in all plastics, such as being light and resistant to deterioration. They may well soon replace copper in integrated circuits in machines that have to be as light as possible, like planes and rockets. Artificial nerves, for instance, made of polymer conductors, could be implanted in the human body. Unlike copper, these polymers would have the advantage of being immune to the natural defense mechanisms in living organisms. Another promising avenue for plastics is polymer mixtures. The principle is simple. If a polymer does not present the desired properties, it can simply be blended with one or several others which do. A shock-resistant polymer mixed with a polymer that is resistant to certain chemicals makes for an alloy that will both be shock and chemical-proof. Such mixtures are already used on a large scale in the automobile industry. Among others, they are used in dashboards and bumpers. An infinite number of combinations is possible with polymers, and mixing polymers holds interesting possibilities. 10 years from now, fully half the plastics on the market will be polymer mixtures. The growing use of polymer blends will probably have a beneficial effect on the environment. The quantities of recycled plastics will increase, since recycling plants will be able to mix plastics which are not worth recycling individually. The last possibility is of utmost importance, considering the damage caused to the environment by non-biodegradable plastics.
Let's hope that the age we live in can accomplish more than to leave to posterity heaps upon heaps of plastic waste, especially since we continue to produce new varieties of plastic combined with other materials to create composites. Composites are new high-performance materials. They're used in cars, airplanes, and even in the protective shields of nuclear warheads. Yet, long before man, nature had invented composites. Wood is one. It's made of a fiber, cellulose, which is trapped in a matrix, lignin, which compresses the fibers and makes them rigid. All composites are based on this principle. We have ways of improving the quality of almost all fabrics and have produced a new category of textiles called technical textiles.
For centuries, man clothed himself in fabrics made from natural fibers, such as wool, linen. cotton, silk. Then, in less than 1 century, everything changed, and most of our clothes now contain synthetic fibers, such as acrylic and polyester. Uses for textiles have also changed. For today, clothes only represent 40% of the market for these materials. Textiles are as easily found in the fuselage of a high-tech plane as in the hull of a racing boat. These textiles, referred to as technical, constitute a thriving industry. The boom is due to the phenomenal development of synthetic fibers. All these synthetic fibers are made from polymers, that is from plastics, which are themselves made from oil. First, the polymer is melted. Then it is forced through a plaque with holes in it. Filaments are thus obtained, which are subsequently stretched and then cooled to yield fibers. Depending on the diameter of the holes and the type of polymer used and products added, the fibers are of different sizes and have various properties. There are plenty of examples of geotextiles. They are used in hospitals, farming, or industry, and even under our tires. Yes, textiles are even used to make some roads more stable. Such is the case, for instance, of unpaved roads used by heavy machinery. When the road is built, the textile is laid down and covered with gravel and earth. The textile, in fact, serves to reinforce the road's foundation. It prevents it from sagging due to poor quality terrain. It also allows for a thinner layer of filler, which also cuts the cost of the road. These textiles here are used for airport and road construction over permafrost, that is frozen ground in the far north. Permafrost presents problems because in summer, after a slight thaw, the ground will be covered with water. The textile, by spreading the weight equally over a very large surface, holds the ground. It's as if the pavement were floating on a huge carpet. All textiles used in the ground or on its surface are called geotextiles. They all possess excellent mechanical properties and are very resistant to chemical and bacteriological agents in the ground. But these are not the only properties geotextiles have. They are also very porous. They are about 75 to 90% vacuous, which makes them an excellent habitat for bacteria. Bacteria can easily cling to the textile in settling into one of its numerous holes. However, on a smooth surface, the bacteria would immediately be swept away. Bacteria are the soldiers needed for biodegradation. Textiles which retain bacteria could be used for the treatment of liquid waste, whether agricultural, industrial, or domestic. They could also, among other things, be installed in septic tanks. Many homes are still equipped with septic tanks. Most of the time, effluent from such tanks is filtered through a trench of sorts, filled with sand and gravel. This system is far from adequate, and the effluent ends up contaminating the earth and even the ground the water comes from. However, if a special compartment were installed near the outlet of the tank, filled with geotextiles, the situation would be different. The geotextiles would retain the bacteria which decompose the organic matter in the effluent. The cleansing process begun in the septic tank thus continues inside the special compartment. The treatment of waste using geotextiles is roughly 10 times superior to what is obtained with conventional septic tanks. Since the first synthetic fiber, nylon, made its appearance some 50 years ago, more than 2,500 new fibers have been created. These fibers have only just begun to invade our lives.
Even though acrylics are now as popular as oil paints, diehards still swear they'll never use synthetic materials to create art. There will still be marble statues, wood furniture, glass and steel will still be used for buildings, and concrete and stone for dams. But increasingly, more and more new materials will be shaping the world in which we live.